Thanks everyone for coming on a Saturday for this talk. I hope you all like the first talk. So we are going to go a little bit more deeper into those things with the concepts, some of the concepts which we have discussed in the first talk, and we will just unpack a little bit more from that starting point, right? Before that, my name is Prashant. I'm a principal consultant in Equal Experts. I've been with Equal Experts for almost 10 years now and been in the industry around 18 years. So I started working with AI a little bit in 2023 towards the end of that. Not AI, I would say LLMs. Before that itself, before that I was dabbling around with some of the machine learnings and things like that. And with LLMs, with ChatGPT, I don't know how many of you have tried that first ChatGPT which came out, and then the first Copilot which came out. So from that time onwards, I was in that area. So right now, I'm mostly working in organizations where we are transforming how we are actually developing softwares using LLMs, as well as how modern world solutions can be created using the LLMs as the forefront, right? So yeah, before going into the talk, I just wanted to see how many of you are token millionaires and billionaires, right?
You have to explain what that is.
So this was a very the new terminologies which was like actually being heard yesterday. There was a conference which was happening, and this is one of the word which I heard, and I was like, find it funny that okay, new world, people are talking about token billionaires. Those are people who are actually exhausting billions of tokens, right? So they are called as token billionaires, right? So basically they are into AI or LLM world, not AI world, specifically into LLM world so deep, they are basically burning tokens, right? So today's talk is gonna be about tokens, right? Or what does it mean? And so what we are gonna do is that we are gonna go in deep, little bit more into the LLMs. And the reason why I wanted to do this talk is that when I started with LLMs, the biggest problem for me was that visualize this, what is happening, right? You might have seen this, like when you're going to ChatGPT and ask a question and it comes with an amazing answer, like as if like you're talking to someone. The moment you go into your coding, right, it comes back as the code, like Python, JavaScript, whatever it is, right? So suddenly when I started with this, the first question which I was asking was that, okay, how it knows what actually made that differences, like why it is actually not chatting with me instead of that giving me code, right? Why it is actually giving me right amazing looking answers instead of code when I'm actually chatting with the ChatGPT. So that actually led me into a rabbit hole of trying to learn more about LLMs, internals of the LLMs, what is happening, why these differences of these things are. And I don't know how many of you have used in your the initial models. If you would have asked it to say that, okay, hey, you are an amazing senior engineer, immediately your code will look different from normal. If you ask it to generate an algorithm and then you just add these 2-3 words, suddenly your code looks much more better. So this is where it was like, okay, hey, how does this couple of words are actually making these differences? Is it real? Is it people are saying that, okay, if you threaten, if you says that, okay, hey, you need to make it right, then suddenly everything will be magically appears right, right? So such kind of things, like when papers were written over there, I was like, how does that possible? Like, okay, simple couple of words are actually making a difference and it is measurable differences in the quality of the output, right? So this is where I started with it. And I felt like, okay, it is really, really important for us to kind of visualize what is going behind the scenes. And that will help us to basically use these tools very much in a very efficient way. So that is what we are going to try to do it. So we will talk a little bit more about what does it mean, how does this different types of things which is happening inside an LLM. And also we talk about how the training works. Maybe we will touch upon one of the questions in the previous ones, right? Like embeddings, how it is actually knowing about these things, right? So we will do that. And we will talk a little bit more about inference time. Inference time is nothing but when we are chatting with or when you are actually interacting with those models, right? And also a little bit about, if the time permits, we will talk about fine tuning. It's a very large topic, I know. I'm ambitious. We will see how far we can reach, right? And if something time is not there, then we can talk after this talk. After this talk, as well as a networking time, we can talk more about it, right? So before going into deep into LLMs, I just wanted to take a step back and talk about, like, today's when people are talking about AI, most of them are talking about LLMs. But AI is not a term which is actually spin up right now. It was there from 1956, right? So artificial intelligence is nothing but if a system can actually do something which is human intelligence was required, it is called as artificial intelligence. A simple rule engine can be termed as an artificial intelligence system, right? So in artificial intelligence systems, when we started in the old days, it was just a rule engines, like created with the rule engines. And then comes the machine learning. What actually it does is that, okay, you give some data and I can actually learn from it what that rules means. So that is when the machine learning comes into picture. It started more going towards the data side of things. Then the next big evolution was deep learning. What happened in the deep learning is that is where the neural networks happens. Neural networks is like similar to our brain neurons, right? Like how does that happen? So neural network is that more like kind of bigger picture over there. It actually gets more data information over there. You can learn these patterns and things like that. And once this neural network, and then is then the evolution of Gen AI or generative AI, and LLM is a part of generative AI, right? LLM is basically on the text side of things. Right now, if you see, you go to ChatGPT, Claude, most of them are multimodal models. What it means that it is not only it can generate text, as well as it can actually consume and learn about the images, videos, and things like that. So this is the generative AI space. So now I just wanted to these days everyone interchangeably use AI and LLMs. If you talk about AI tools, it's basically most of them are actually talking about LLM tools, right? So with that in mind, I'm not going to talk more about max in this talk. Like who would have thought that, okay, hey, sometimes when we learned about trigonometry, we are going to hear more about that in today's world, right? Like, so I'm not going to talk about a lot of max about the LLMs. I wanted to try to bring it down a little bit to a layman terms so that we can actually visualize in our head. But these two things is absolutely required for us to talk about it. One is vector and other is matrices, right? And vector, you already heard from Tamina about the embeddings and the vectors and all those things. So it has a list of numbers, right? And it has a magnitude, it has a direction. And matrix is nothing but rows and columns of these vectors. You can think in that way. That is good enough for us to go in deep into the LLMs. So on a high level, on a 10,000 feet, what does an LLM looks like? So you give an input. The moment you give an input, there is something called a step called tokenization happens. And once the tokenization is done, then you will embed it, which we talked about a little bit about in the previous talk. After that, we will do something called as transformers. Don't worry about these boxes. Right now, we are going to dig deep into each of these blocks, right? And then there is a prediction. And that is when the output comes in. So each layer has its own complexities, right? Each layer has its own. You can actually create talks on each of these boxes, 1 hour talks. It's that big topics, each one of them individually itself. So how does this entire ChatGPT world, or like suddenly, if you are into this space of AI deep learnings, there was nothing much happening in that, and then suddenly one day it exploded. And that one day was this one paper called "Attention is All You Need." This paper came out in 2017. This actually talked about a new type of an architecture, how the transformers. So that was the foundation of the LLMs. From that time onwards, then the growth in LLMs was exponential, right? And what it was actually doing inside, it is very simple. So till then, you try to predict the next word. There was so many algorithms of predicting the next word. But this paper actually introduced a concept of trying to understand the meaning of a sentence. And it do it in parallel, right? That was a huge change, that immediately what happened was that the scale at which we can learn about the entire the internet has actually reduced by large, because you can do it in parallel, right? So this paper is the one which is actually changed the landscape of LLMs. So I will highly recommend people to read through the paper if possible. And there are a couple of amazing videos in YouTube by Andre Karpathy, the person who actually introduced vibe coding term, right? So he has a 3-hour video in YouTube, which actually help you to build a nano LLM in your machine using some of these concepts, right? So this is an amazing paper to do it. So we are going to go deep into each of these blocks, try to understand it, and then I hope once after this talk, you can go back and go through those videos, and that is amazing. And there is one more call out which I want to do, which helped me a lot to learn about LLMs, is one of the Indian startup called Vizura. They are a Pune-based startup, and they have amazing free YouTube videos where you can actually learn about inside LLMs and what you name it, they have a video about how to learn, and they explain in depth. So for LLMs, I learned from them. It was around 50 hours of free YouTube video are there to learn how LLM works, DeepSeek works, how the different types of model works, and all those kind of things. So please check out them as well.
Can you spell it?
Vizura. I can share it with after the talk. Yeah. So one more thing before we go deeper, just wanted to differentiate between the training and inference. So the training is when the models is getting intelligence. So it will actually try to learn from the existing data set how to predict the next word, next token. And inference is when these models are going to put that into work. So inference is when you basically get a new set of words, new set of things, and then suddenly an output is coming in. So just keep in mind this distinction of phases. We are going to talk more about the training when we are starting, and then we slowly move into the inference side of things at a later point in time. Cool. So now going deep into our topic, we are going to unpack each one by one. The first box in that 10,000 feet was tokenizations, right? So what actually is happening? I'm going to take an example over here. The dog chased the ball. So you will see this example throughout the talk as well. So what is happening in over here is basically this entire sentence is actually converted into different tokens. And in this example, I would say the dog chased the ball. All of them are different tokens, right? That doesn't mean that in this example, I said that, okay, hey, these are different tokens. Each word doesn't mean that it is an equivalent token is there. A word can actually be split into multiple tokens as well. It depends upon the algorithms, what you are going to use it. It depends upon what type of embeddings you are going to use it. So the dictionary which Tamina was talking about, 348, the dimensions, what is over there, all those things. And then she also talked about a dictionary of 10,000 words, right? So that words or that dictionary also matters how these tokens are created. To give an example, in GPT-3, you have a dictionary of 50,000 and change words, and you have around 12,338 38 different dimensions inside a vector. We'll come to that a little bit, but the point which I want to make it in this is that the word, when a sentence is actually, when you enter a sentence into any models, it is actually divided into different tokens. A word can be divided into multiple tokens. For example, tokenization, right? That single word can be divided into 2 different tokens, which is token and ZATION as another token. Right? So this is the first step to happen, right? So this is like, how do you know how to divide it into different tokens? Because you have the dictionary, and the dictionary will have all the tokens which is out there, and it will try to find the tokens which is there, and then get the ID of that particular token. So for example, in this case, in the first and the fourth the place, both of the will get the same token ID, because there is only one token which is the over there, right? So once you have the ID, then you will try to convert that into vectors. So now you have ID, right? Because even before going into this, why do we need to do this, right? The computers only knows about the numbers. It doesn't know about the words. So we are trying to represent these words into numbers so that computers can actually understand this. So now what happens is that, let's say this is a dictionary of 50,000 tokens over there. So everything has an ID over there. And each ID, there will be a representation, a vector representation which is out there. So over here, you can see some of the examples which I put over there. dog, cat, apple, and orange, right? So all of them will have its own representations. So in GPT-3, you have 12,338 dimensions. That means that each those numbers, right, can represent each fact of that particular word. That is how it is trying to learn about what does this mean. And what actually happens is that when after the if you plot that into a n dimension space, the similar meanings will come together, words will come together. So that is what the cosine similarity and what the previous talk was talking about, right? So how does it actually, what does it mean? How can you actually interpret it? Let's say, for example, I am going to ask every word which I am seeing right now, are you an animal? Right? Are you a livable thing? Are you a fruit? Like if I ask such kind of questions, I will get an answer. Some things will be closer to that, right? Say for example, that is what I was trying to pretend over here. Is like, okay, hey, the first question which I am actually asking is, are you an animal? And for dog and cat, it will be closer to one, which is like, yeah, I am an animal. But the next is, are you eatable? Let's say the question you are going to ask is, are you eatable? Then of course, dog and cat, maybe, I don't want to talk more about it, but so you get the gist of it, right? So that is the kind of things which is happening. But are these the real questions which we define when we are creating these vectors? No. We don't know about any of those things. What we'll tell is that, hey, you have a list of thousands, millions of, or trillions of data which is out there. Now you go and look into those data, and I want you to represent these informations in a 12,000 different vector space, dimension vectors. That's all what I'm giving the objective to the model. So what happens inside that is that it will go and try to, I will take one small example of it. It's a word2vec, it's an embedding model. It actually uses two type of tricks. What it does is that it will look into the sentence which is there, the dog chased the ball. And what it will tell is that, okay, hey, when you have the dog, predict the next word. So what actually it is trying to do is that it will predict the next word, and it will change that matrix things, so that anything which who can chase will all come together to very similar spaces. So that is how they will learn about it. So in nutshell, after the learning of the embeddings, usually the embedding, this matrix is also self-learned. When you are actually using the latest models like GPT, Claude, or whatever it is, they train along with this transformers, they also train the embeddings over there, right? So you can get some small embeddings for you to play around. I will highly suggest that the game, which the ladder game, because that will help you to learn about a little bit more about the conceptual part of how the embeddings works as well. Yes.
What algorithm makes these numbers for dog 0.98?
Okay. So there are multiple things over there. I'm not planning to go in deep around it, but usually it is around gradient descent and backpropagation, how you will actually end up doing it. So when you start, you will start with random numbers. Like there is no meaning over there. And then what you will do is like you will predict next word. And that prediction will be amazingly wrong, right? It is very wrong. Then you will find out how far it is actually wrong. And then you will just tune that a little bit and then again predict the same thing. So it will be thousands of millions of steps, which actually happens in this incremental way. And you will see that, okay, hey, whether you are going towards the right side or not. If you are going towards the right side, that is very similar thing, that semantic ladder thing. If it's going to the right way, then what you will do is like you will tune it. If it is going in the wrong direction, then you don't change anything. You will try it again, right? So that is the algorithm which is doing it. So what usually happens is like you will, this is where it all gets, like the LLMs are next word, next token predictor, not even next word predictor. It's a next token predictor, right? And what it does is like it predicts. So during the learning phase also, it predicts the next word. When it predicts and it gets wrong, it will tweak a little bit. So then what happens when you are doing it for trillions of times, suddenly some kind of meaning starting to appear. And is it like many of the things are actually, if you see, like after the embeddings are created and then you represent, like one of the most common example people uses is that queen minus king is equal to women minus men. So there are two different, like 4 words, they all have a different vector representations. But if you try to do another arithmetic expressions like minus and things like that, you will get very similar answers to it. And it is not designed like that, but it is actually when you do it again and again, because all these things, like say for example, the queen and king is actually used in a very similar context. It started to learn about that from this because there are 12,000 feature space, you can actually start seeing some patterns emerging over there. So it is an emerging informations. So these numbers are actually goes through a lot of training, and then these numbers will be an emergent of that particular training phase.
Yeah, so just one question. During the learning phase, what is the evaluation process? Is that self-evaluation works? I mean,
So this is where
When
maybe I can actually show a little bit in later, and then I will come back to that question again, because we have a slide about how this is actually happening, and then I think it will make more sense when I'm talking about over there.
Yeah,
So I'll come back to that.
Yeah, the quick question. The transformers have the capacity to do the evaluation as well, or is it a different architectural layer? Does it?
It is not like that, because
Okay.
it's again the data is predetermined. It is actually the data which is trained is on the internet. So you have the next word. You already know what is the next word over there. So use that to say that how far it is from that word to this word.
Okay, I'll wait for that.
Yeah. So what does it actually means like for the embeddings, right? So as I said, it's a very high dimensionality. Like GPT-3 is 12,000. In new world, the new state-of-the-art models, we have no idea what is this dimension means. These days, trillion parameters is nothing. GPT-3 is only 175 billion parameters, right? For that, there is a 12,000 dimension of vectors. So the latest models could be trillions and trillions. So these dimensions might be even higher as well. So it is really difficult for us to understand it because it is in closed source. But yeah, so it's a very high dimension in that space. The mental model which you can actually take it is like, okay, hey, when I see a word, I want somehow to represent that word into a mathematical equations or mathematical representations. How do I do it? I might ask like 12,000 different questions, and I will keep asking those 12,000 different questions to the same 12,000 different questions to each and every word which I'm going to come across. And each will have a different answers to tell me. And that is how I will create that. And one point in time, when they are actually getting it right, this kind of emergent behaviors will come across. Like all semantically correct, semantically similar kind of words will come to start grouping together. And you will start seeing this, okay, how far it is, whether it is strongly semantically strongly aligned or not. So this is what about the embeddings. So now when I see a sentence, the dog chased the ball, I said that the has the same embeddings, right? So the dog will have the like, even if you are using the dog in anywhere, right? Man bites a dog, dog bites a man. If you see these two sentences, right, it's same words, but the position actually changed the meaning of the entire sentence as well, right? So what actually is required is not only to semantically represent a specific word, it also needs to know that, okay, where exactly these words comes in a sentence. Then only it can actually understand the meanings of it. So that is where the next things comes in, which is positional embedding. So what it does is that it will add a positional information into that particular vector, right? So you have an embedding vector, the dog, the chased or ball, the bites, all these words will have its own embeddings. Now I will add a little bit more information into it, which is called as positional embeddings. So this positional embeddings can be of different ways. There is a different space where people are researching how to positionally embed it correctly. I mean, how easily you can actually do that and how efficiently we can do this positional embeddings. But to minimize the mental overhead of that understanding purpose, you can think about this. Let's say each position will add some kind of information to that vector to represent that, okay, hey, you are in the first position or you are in the third positions. So that information has been encoded in or added into the existing embeddings. Now, after this phase, right? Once I added the positional embedding, you can add it as a vector addition arithmetic. You can actually do a directional, a rotary based directional kind of a thing. There are different ways of doing that. But the thing which we need to learn about is that once you have embedded this information also into the first vector, now you can differentiate between dog bites man and the dog vector in the first sentence, man bites dog. The dog vector in the second sentence will have different outputs after these steps because you have some kind of positional information been added into the vector of it. Right? So once you have this, you are ready for the next big thing, which is transformers. And this is what attention is all you need. Paper actually introduced it. Right? So it is called as self-attention. This is where, see, like we already understand the semantic meanings of a token. You understand what that meaning means. Like, okay, hey, apple means might be a fruit, whatever it is, right? At that point in time, apple have a vector. That's it. Now, you need to understand in what context you are actually using it. That gives you contextual meaning to that particular word, right? So now, if I'm saying that, okay, Apple is an iPhone, then it understands iPhone is an Apple's product. You know that, okay, that is not a fruit apple, but a company apple. So this is where the contextual meaning comes into existence. The self-attention layer tried to capture that contextual meaning of a particular vector. Right? So we already got the semantic meaning. Now we are going into the contextual meaning. How do we do this? Right? This will be so in this case, again, to simplify it, we'll go to the basics of how the transformer papers actually presented it. So we talk about 3 different matrices, which is query, key, and value. And what does this means and what it does? Right? Every one of us actually have done a Google search, right? You have goes and then search for something, and you will have a list of results which is coming in. Then you will have a header which says that, okay, what this result is gonna give you about it. You will skim through that headers and you will find out, okay, this is something which I want to know more about it. You will go in deep of that particular result to get what you really wanted it, right? So what it actually, you can think of it as like similar kind of things. Query is asking, hey, like when I am seeing a word, maybe it is going to ask you like, okay, who have an influence on me? Like say for example, I think maybe I will show you a video and then we will talk more about it. Right? So this one, each vector, like each word has a vector over there, and it has 3 different matrices: query, key, and value. One is actually, hey, what I'm actually going to look for, what I'm going to offer, and the other is what is real content is. So what it actually is doing is that the chase vector, what it asking is that, okay, hey, is there anyone who is actually meaningful to me? The word the, I don't care about it. Chase can be by a dog or by a ball, right? So what it actually happens in this case is that the word ball and dog will have started to influence that chase vector. And I will let you just go through this once and then we will start talking more about this. Right? So what actually happened over there? So in a sentence, there are multiple words over there. Each word asks these same questions. Hey, whom I can actually attend more to it? Who has more meanings to us? Who can give more meaningful information to me? And if someone is actually ready, or someone is saying that, okay, I can give that more information to you, then they will give that particular information to that particular token or that particular word. So now that word will have more information about that particular sentence itself. And that is how the self-attention works. I'll take a pause over here. Yes.
Maybe something related to the architecture itself. I would want to know why they would zero down on only 3 values, just QKV. For example, you could solve the same problem with q and k or q and v, or you could have another, let's say, lambda, which could give you more information about the sentence structure and who belongs to which word belongs to or relates to what better. Just that, yeah.
Cool. Why some of those things? Why is there is like no answers for it, right? It is basically a research paper which they tried to use that. Okay, they wanted to use 3 of them, and they started playing around with it. These days, it actually has a different algorithms which is coming in. Optimization of key, query key and value is happening, right? Maybe some same this query and key matrices have been used for this latest different types of algorithms as well. But if are asking me very specifically around why only 3, why not 5, or why not 2, or why not 1? So basically, there is no answer for that, I would say. The thing what they were actually looking for is that, hey, start somewhere, and then can we actually encode enough meanings by using this or not? So what they have tried is like there are 2 things which happened over there. One was the matrix has a hard dependency. The matrix multiplication when you are doing, right, you need to have a similar dimensions to it, and that dimension is fixed. Over here, there is a 12,338 dimensions over there. So that dimensions is when, yeah, you need to go a little bit into the maths for that. That dimension is all over the places. All the different blocks is always defined by using that dimensions. So that dimension needs to be equally divided into some places. So it could have been done to 2, but not to a 5, for example. Right? So that is also one more reasons why it is actually 3. Right? So not 5, for example. And sorry, that was the question, right? Like, did I answer it or?
Close, yeah. I think yes.
Okay, we can talk more about after the talk as well. So what happened over here is that when you start, that the training phase starts, right? None of this has any meanings to it. It is just that, okay, 3 different matrices out there with random values over there. Nothing over there. Then what is going to happen is that you will start getting these words or these sentences from your corpus of informations which you scrape from the internet, trillions of data which you are going to get it. So then what it actually going to do is that it will start trying to predict what is the next word is going to be, which will be always, again, the same embedding prediction which is happening over there is going to happen over here as well. Here, it is a slightly different over there. There, the prediction was based on only that one single vector, which is actually 12,338, right? That is the only tunable parameter over there. Over here, now you got 3 different matrices and all those parameters which you can actually tune and change it. So what it does is that, say, for example, maybe let's assume a hypothetical situation, right? Like, say, like let's say I am actually seeing a sentence, Prashant is awesome, right? And the questions you should start asking maybe is that, hey, is there an adjective like who is, like, let's say we are talking about the token Prashant, and it start asking, is there any adjective for me to attend to? So it will say that, yeah, it is there. Is it a person's name? Yes, it is there. So that kind of meanings, you will start asking these kind of questions. That is where the query comes in. And when a query has been asked to all the set of other tokens over there, the people who are actually give more importance or attend to it, they will say that, okay, hey, I have something which will be useful for you. That is where the key matrix comes into picture. Key is actually trying to tell it, saying that, okay, hey, you need to consider me. I am actually going to give you more meaning to it. Once these 2 informations are there, you will choose the value matrices of it, and then you will scale that value matrix based on whatever things which is there. So that is where the percentage comes into picture, right? Like how much you need to scale these informations. Once this is created, then you add this also into the initial vector, embedding vector which we created using the positional. Right now it's until the positional. So you add all this information back into this one. So now you got a contextual meaning also in that vector is actually now enriched with the contextual meaning as well. Right? So the advantage of these matrices and things like that, how do I attend? When I say that, okay, how do I attend to it? right? This is where matrix multiplications and things comes into picture. When you are actually doing a matrix multiplications, you are adding more informations into it. So, for example, you are actually deviating a vector into a specific directions, so that you are saying that, okay, hey, this vector has some informations about this, so I need to slowly move towards that particular space. Like, say, for example, apple, a fruit, and apple, a company, may have a two different sentences, right? Like, I can eat apple. Then what happens in the apple vector is that I will slightly move towards the fruit side of things, away from the company side of things. But if I'm talking about apple in a company context, what happens when this query key value matrix and this addition of this information is added to the apple, it will go towards the company side of things, right? So now with that meaning, you can understand, okay, hey, apple in this case means about a company, right? So this is where one of the first question which I asked, right? Like, how does the couple of words can actually change the output, right? So when you are saying you are a software engineer, rather than simply asking a code, I write a code over there, what is happening is that you are slightly changing this matrices of each of these words, the meanings of these words, into towards the coding space of things. So it will then start looking into the coding side of things, like, okay, hey, Python, Javas, and code tokens, the tokens which are more tending towards the code side of things, right? So this is where the meanings, like the words which you are putting into your prompts really matters. So this is how the learning itself is happening. So when the learning process happens, this will go through this process like trillions of times. It will go through this, it will create this vector. It will initialize with random values of all these matrices, and then what it does is that it will change. It will say that, okay, hey, this is, we will do the multiplications. You will add this context. With this context, can I actually predict the next token correctly? If I can't predict the next token correctly, what I will do is like, how far is this next word? Like in this case, let's, for example, the dog chased the. That is the sentence which it is actually looking at, and I need to predict the ball as the next word. So when I actually embed this meaning into it, and then I predict the next word, if it is not ball, that means that I will come to know that how far. Like, let's say the first prediction was the dog chased the, and then some random word, right? Let's say Bangalore. Right now, I will find out how far it is from this actual word, which is supposed to be ball, right? And then what it does is that, okay, this is this far, so I need to make some small changes to it. So that is where it will go and change or tune those models, the parameters of query and key and metrics, those metrics values a little bit, and then predict again. So now think about, there is one more sentence, right? The dog chased the stick, for example. That is also a valid sentence, let's say, right? So now what happens in this case is that when you see different types of variations of the same meaningful things, they all try to come together into one single space. Then slowly you are moving towards that space where similar words, similar contextual words are sitting together. So you are trying to nudge your application, your all these matrices, all these values towards that space. So now this is one single thing, right? Like, so you might have asked in this particular case, your query is basically say that, okay, hey, what is the adjective which I am looking for? Is there any adjective in my sentence? This is one of such kind of matrices. You could ask thousands of such kind of questions. So that this is where multi-head attention comes into picture. So what transformer paper actually introduces is that we can parallelly do this multiple times. And what it is help is that it will try to create more meanings from the context which has been there in the sentence. It can ask multiple different kind of things. What type of things it is going to ask, we can't really say at that training phase. But when you are actually, once the training is over and things like that, if you represent these things into spaces, you might see some kind of patterns. But those patterns are not really like that meaningful, I would say. It is just for us to understand, hey, there is some patterns it is going to learn about it. So what happens in this is like this increase or the multi-head attentions, what actually help is that you will be able to represent it in multiple different ways. It's not just, okay, whether I have an adjective over there. whether I have an animal over there, or not like that. You have multiple things which is happening over there, right? In each matrices, it will have different weights over there. So all those informations together, that's the scale of large language models. It has trillions of sentences, it has seen it. And when it actually is seeing those things, it will be able to go through all these different parameters. And I can change all these one as small by small bit, and then try to create or enrich that information more and more information into this. Cool. So once you have this contextual meaning, which is enriched, all right, into that one particular vector. So now I have got the semantic meaning, which is coming from our embedding. I know about the positional side of things. I know about how the context of this entire sentence is. The next one, what I want is that, okay, how do I understand what would be the next prediction word would be? So this is where the biggest or the most complex bit to explain as well is comes into picture, which is called as a feed-forward network. And in this, what is actually happens is that you will try to project this information into a very high dimensions. What it actually helps you to do is that encode more information into a space, vector space, or a high dimensional space, so that you know that, okay, you can capture each and every single meanings of those words. Or even, like, say for example, Michael Jordan is actually playing a basketball, right? A basketball player. So where this information has been loaded, right? It knows about it. It may not, Michael Jordan might not be there, that as a basketball player may not be there in the context of the sentence at all. But it has been in, like, when you're asking a factual questions, or when you're asking some of these things, it knows about it. It doesn't comes from your context of it. Where this learning happens, where is this information is encoded, right? This is where the feed-forward network comes in, and this is the neural network or brain of the system, which is over there, right? What it does is that it will, right now we talked about 12,338 into 50,000, what are the numbers? It is some like small billions of the small billions, like 1.2 billion or something like that parameters is what we are talking about. But this is the layer which will project this entire thing into a higher dimension. First, we project those into a higher dimension, and then you come back to it. And what it actually helps you to do is that you will be able to encode more informations or more facts into this learnable parameters. So this is where it will get more information to how it learns about the facts and things like that, right? So in this, what happens again, this is also a feed-forward network is also a parameters which has been tuned. So when we hear about the trillion parameters, billion parameter models, so these are the where the majority of them actually sits, right? Like the feed-forward network. So that is a huge space where you can actually inform, put some informations into it, and it will, it will mathematically represent the meaning over there. And you can actually go to the next one, which will be that when you compress it towards the next token, which will come back to that our 50,000 tokens. At that point in time, it will give you some kind of information about what could be the next word token, which I can actually predict, right? So in here, what do we do, right? Inside the training time, what happens is that you will ingest the data, of course, you will give this information, you will have this entire sentence, the dog chased the ball. What happens is that it will convert this one single sentence into multiple sentences. It will start with the as a first training input, and it will try to predict the next word, which is the dog. And then you will give the dog as the next input. It will try to predict chased. And the third will the dog chased, and then it will try to predict the again. The dog chased then they predict ball, right? So you got the gist of it. So a single sentence has been actually divided into multiple training sets. And what it does is that it will give these inputs into it, and it will do billions and billions and trillions of times. The same sentences again and again. It will try to predict the next word. It can't happen. It will go back. It will try to how much, it will find out a loss function, like how much deviates from the real result. That is called as loss function. and it will change a little bit, it will tune a little bit side of things. You can think of this, all these are knobs, right? Like different knobs. You will tune a little bit on here and here. You might be need to tune only the like what is like hypothetical case, right? Like you have like 10 knobs over there. Sometimes what happens is that you go and change the 5th knob, and the next iteration it will be really bad. So what you will do, you will turn it back, and then you will go and change the 6th knob a little bit. You will try to do it in the 2nd knob a little bit and 10th knob a little bit, and then you'll see how the words are coming up. So when you do this exercise in parallel in multiple trillions of times, that is when you will get all those tuned parameters and start predicting the next word. So once you have done that, right? Like once you have that training is done, let's say it is actually just predicting the next word over there. What happens after that, right? This is where like a real inference side of things comes into picture. What happens is that when you are predicting just the next token, right? You will not gonna get these answers. Like say for example, what is the capital of France, right? You will get Paris as an answer, but it defines like whether it is just a fact which is gonna come in as Paris, or the capital of France is Paris. What is coming up, we don't know. It might be just the Paris which is gonna come out of it. So this is where the refinement steps comes into picture. What happens after the model is trained with all this information, you have this model weights and all those things, it will go through another set of learnings, which is actually called as like supervised fine tuning. Different techniques are there. What it does is that, and also there are some like reinforcement learning with human feedbacks. So what it does is that, okay, it actually predicts something. Say for example, I will say that, okay, in ChatGPT, I need to give us an answers, right? Like in a human readable format. If I say like what is the capital of France, if it just says Paris, maybe I don't like that. That may not be what my intention was. My intention was that the output should have been the capital of France is Paris. So what you will do is like you will start giving this information back to LLM, saying that, okay, I need you to predict like this. This is where fine tuning comes into picture. And this fine tuning can happen in multiple ways. Like supervised is like, okay, you will have you know that, okay, how to do that. You will give examples of it, and then you will ask it to, okay, now you need to start predicting like this. And the feedback is when you might have seen this many of the times, like when you go to ChatGPT and you ask a question, you will get 2 different answers, and you will ask like, hey, which one do you prefer? So such kind of things, what is actually is asking for is human feedbacks, right? Using those feedbacks, you can train the model to predict in that way, right? So these are the techniques which actually happens the next, like, all right, okay, this is the format which I want to do it, and things like that. So that inside that you will start forming some of those, the way how we see the output is coming. Like the coding models is a very specific model which I want to always want to get code out of it. You will start seeing in this, when you are doing a fine tuning, you will start giving more outputs as code examples, things like that. And once you have done all those kind of things, right? Like, so if I ask the same question, right, like multiple times, you will never get the same answer. If it is always based on the prediction, the next token, I will always know that, okay, what the next token is going to be, because there is the highest probability of that particular token. I says that, okay, hey, this token is the highest probable, and if I am actually giving that output always, right, in that case, then whenever I am actually talking to LLM, I should get a deterministic output. So this is where the generative, that is not a generative thing. Then what it actually does is the parroting what it actually learned in the training space over there. Right, in the training time, it actually seen something. It is predicting what is the next one based on the training data which it is having there. So it is not generative, it is just parroting what it is learned. So to become generative and to become creative, so that is where the probabilities and samplings comes into picture. So there are 3 knobs which you can actually understand. If you understand that, you know how to change the model's output. Those are like temperature, top K and top P. Temperature is nothing but very simple thing. Like say for example, if temperature is 1, the probabilities which I'm going to get will be exactly same what the model is predicted. But if I actually give it's a scaling factor. You can think of that like that. If you have a temperature as like 0.5, it has like, it just multiplies what is the output of it, and it will basically scale output into the next level. So you can actually think of like, if temperature is 0, you would say that, okay, hey, there is basically nothing, no changes is going to happen over there. Sorry, if it is temperature is 1, it is actually no changes which is going to do for the output of it, but it will have impact on the top k and top p, which will also which also has a say in what is the next word which is going to be there. So top k sampling, what it does is that you will say that when you try to predict the next word, we said that okay, there is a dictionary of 52,000 words. So every word will get a probability over there, and all those probabilities will be added into one, right? Like, because probability, right? Like, so it should be added to one. So every single one will get some specific numbers, right? Maybe 0.00001. It could be that also. But every token get a probability over there. But top K, what it says is that only consider the top 10 of those words when you are going to predict in the next as a next token. So what it does is that it will only find out the top 10 values out of it, and from that 10 values you will predict the next word. Top P nucleus sampling, what it does is basically is that, okay, hey, I don't know how, like sometimes what happens is that the next word, the numbers will be very similar to each other for whatever reasons. Let's say 0.05, 0.049, 0.048, like that. Let's say all these numbers are like that. So when I said 10, top 10, you will lose that some numbers, even though 11th might be very close to the first number itself. But still you are going to lose that out. So instead of that, what you could do is that you can actually create something else. Like, say for example, consider all the tokens whose probability will be added up to 90%. So now you will dynamically consider, say for example, if you are really clear about what is the next word is going to be, you will have one number which will be a very high probability space, which is 0.8, right? And then another numbers might be, another tokens might be is like 0.3, 0.01, 0.02, 0.05, something like that. When I say that, okay, hey, my top P sampling is 90%, I will only consider those maybe 3 or 4 tokens, which actually when you add the probability, it will come to 0.9. Right? So that will give you a little bit more dynamic feeling of it. So if you can't predict the right word, or like it can't really give it, this will give you like, okay, hey, consider all those things which will come to the 90% probability from the top, and then you will use that list of words to predict the next one, right? So this is how the predictions works. So I said that in the initial starting of it, I said that, okay, LLMs are next word prediction tokens, right? But we talk about AGIs these days. We talk about reasoning. You all have seen that, okay, LLMs can actually reason about it, right? Like we talk about like, oh, this is actually understanding what I'm trying to tell it. It tells that, okay, I'm looking at this, I'm looking at that, and then I'm trying to find out the answer for it. So reasoning is basically a method or like way to tell, like, which happens in the fine-tuning space, where you will say that you will create something called as like thinking tokens. So what it actually happens is that instead of immediately answer the answer to the question, it will start creating tokens which looks like kind of thinking patterns. So this, what they do is a technique called as RLVR. What it does is that it will create a model, reward model, which will tell that, okay, your function or your, one of the question was around the evaluation, right? So this is where it is actually telling that, okay, hey, your objective is not only to give the right answer, but also you will get more reward if you can actually reason it correctly. The tokens which is coming in the thinking space, if it is actually aligned with what we are actually after, then you will get a more reward to it. So what happens in this is like, again, even though this is a next word predicting, but it is predicting the next thinking token. So at the end of the day, it is not really thinking, it is just predicting it. the next thinking token over there, and it has a chain of thinking what it is doing it. And you can do that by using that fine tuning. And even some of the examples, right? Like you could do even this kind of behaviors even in the prompt engineering if you can actually do it, right? You can slightly say that, okay, hey, I want you to reason like this, and suddenly the model will try to do it like that. And this is the reason why it is like, it is again predicting the next word, next token, but in a very specific way what we told it to do that. Yes, Rubak.
So I think there are two things happening here, right? Like one is obviously the next word is getting predicted, which we have seen like how we can optimize for. There is also the entire response that you get, which you lightly covered about uh, SFT or RLHF, right? So, from a learning perspective, how is like training it for the entire output uh, getting mapped in the model itself?
Okay.
I hope the question is clear.
So I think your question
I'm
is,
trying to differentiate between the next token prediction versus the objective mapping or objective learning.
I don't think that I understood the question really well.
Maybe we can talk later.
Okay,
about
yeah,
this.
sure. We'll come back to that then. Cool. So once it has been, why it is really important, like, so you can actually like supervise learnings and the pre-training and post-training, right? Then you train all those kind of things. You basically create a model which you can actually understand the generic text over there, out there. But what you could also do is like you can do some kind of fine tunings. What it does is that, like, so if you wanna train a little bit of, like, you can change these matrices, what we talked about, right? Different types of model weights are there. You can host that weights in your machines, or like, of course, if you have machine that powerful enough, you can use that weights and then use a technique called fine tuning to change it into your domain. So for example, I can create an open source model, which is like, I don't know, like DeepSeek or something like that. What I can do is that I can always make it sure that, okay, it will give me a JSON output by doing a fine tuning to say that, okay, hey, this is the output which you need to give it. Multiple examples, I will give it to it, and then do some fine tuning around it so that I can actually get that objective out of it, right? So what it's doing is that for time is fine tuning is that we are actually changing this model weights a little bit more to tweak in such a way that it actually output the way how we want it to be. So this will also give more importance towards your domain. So if you have a domain which is very niche, and you want to make the models to understand your domain very specifically, and you want to answer in your domain terminologies itself, you can use these techniques to steer that knobs a little bit more, right, towards your domain, and that will output the tokens that will output the tokens which is there inside your domain in itself. So some of the key takeaways, right? Like what I would say is that, again, going back to the probability engines, LLMs are nothing but next word prediction token. Right? You can change it into this really thinking models and things like that by these kind of techniques of fine tuning and things like that. But at the end of the day, it is a token predictor. It is not a magical thing. So why it is really important? The reason why we all should aware of it is because what you are actually giving to LLM really matters. The context you are going to give it to the LLM defines the output of your LLM. So when we come back to our coding and when we see people are saying that, okay, hey, the outputs which is LLMs are actually giving me is really bad, you should start thinking about, am I actually giving the right direction to the LLM to create the right outputs or not? So every single thing which is out there in your prompts is going to have a say in what is the next word is going to come in. So if you give a very bad inputs to an LLM, you are going to get bad outputs from it. So you need to be very careful about what you are actually giving it. And
So when you talked about tokenization, right? Initially you start with a random number where there is an array of multiple floats. So over a period of time, it goes through a known set of facts, maybe the Wikipedia or the entire internet, and eventually comes to a conclusion. These are grouped together, like you said, king minus queen and is equal to men minus women. So all these are known facts according to dictionary or Britannica websites or all this. So what happens when you give it wrong inputs? So does the embeddings, which are set concrete for some time, do they change internally?
No. What happens when you're giving a wrong input is where the attention, the second point which I have mentioned, right? Attention mechanism has a say in it. Because not only the embedding, right? If you think about it, embedding is the starting point of it. That will get enriched with the position of it, right? And then it will get enriched with the attention mechanism or the contextual meaning of the words. So all these things has a say in how the feed-forward network is going to work on it, right? So that will have a say in what is the next output word which is coming in.
Okay, so if you look down deep into the database, right, the vector database, you're saying the embeddings for each individual word will always remain the same, given
Correct.
you're talking about a single set model. And if you're giving different combinations of sentences, will there be separate embedding vector that will be saved for that, or it's done on the go?
No.
Stateless.
So I think I didn't mention that. Like this is one of the difference between the training and inference. During training time, what is happening is that it will predict the next word, and then I said that okay, it will go and tune the parameters a little bit, right? So this is the learning phase, or training phase. Once training is done, these weights will never change. No. It will be exact same values until unless you choose to fine tune it at a later point in time. Even if you want to fine tune it, like a model needs to be put into the training mode. So a model can be put into an inference mode or a training mode. So inside the training mode, that is when you can actually go and change these knobs or these matrices, values of these matrices. But during the inference time, that is what we all do when we are actually talking to all those models. During that time, none of these matrices will change. The change which is happening is your sentences, your prompt, what input you are giving, that actually has a say in it. So based on that, all these weights has a say in what all things are there. So your input has a say in how this output is going to come in. And no, it will not create different embeddings. But if you can actually look at after the attention layer, the word which you are going to give and the sentences which you are going to give, even a small changes in it, right? It might give a different type of metrics out of the attention layer.
Okay.
Right?
So if I remember this correctly, this happens at the inference layer, right?
Correct.
All these runtime things, and whatever you give it, this is stateless and it's lost.
Correct.
Right.
Correct. Okay. So this is why that is an amazing point as well, right? LLM are stateless; it doesn't know the memory, and there is a huge ways of work like memory, how to create memory via markdowns and things like that, right? So LLMs are stateless machines. So you gave an output, that's it. It doesn't know about it. The work which happens behind the scenes, like ChatGPT and all those places are there, they collect this informations in the server side, right? The question you are asking and then the answer what the model is giving you, they collect this information if you are not on a paid model. So and then what they do is that they collect all this information. That is their training data set for the next versions. Right, so that is when the ChatGPT 4.1, 5.3, 5.4, they collect all this information out of it and then they train it based on that. So during inference, it doesn't make any sense, but it has a say in when the next version of it happens.
Understood.
Cool. So the last two slides before moving in. So these are some timelines which I talked about. It started in 2017 when the transformer paper or attention attention is all you need, that paper came out. And then 2020 ChatGPT 3 came out and the paper came out, and that actually has a big say in the LLM's evolutions. And then the human feedbacks comes into picture, and that is reinforcement learning which happened. And then the mixture of experts models and reasoning models comes into picture into 2004 and 2005. So these are kind of evolutions which happened in LLMs. If you want to learn more about it, these are some of those buzzwords which you can actually go in deep around it, right? I'm not going to touch more on this one. And these are the things which I conveniently didn't talk about and skip part a lot. But if you want to go deep, these are the things which you need to understand. What does softmax means, how normalization work out, what is a dropout, residual connection, gradient descents, and back propagations. Right? So we talked about tuning the knobs a lot. The two processes which happens is gradient descent and back propagations, right? And softmax is where the probability, when all this matrix multiplication happens, after the matrix multiplications, it actually converts into the probabilities. That is where the softmax comes into picture. So these are the places where you can go deep around it. And that's from my side. Thank you, everyone, and open for questions.
So one more question on the same lines. So like as an user who usually prompts these LLM models, gives some use case and does that, LLM has a fixed data set where there are a lot of tokens or embeddings, all this.
Correct.
So you want to give it real-time information by going through a web article or something. So that's
Correct.
when maybe you call it RAG or whatever. So is this mixing of embeddings that are already known plus what is given on the go are done at the inference layer?
So it's like that is really amazing, right? Like if you think about it, in GPT-3, when we say that okay, hey, there are only 52,000 tokens or 50,000 tokens change, right? That means that the entire world of internet you could actually represent in this 50,000 tokens.
Okay.
So that is the fun part of it, right? Like it is a little bit like, okay, hey, is it really true? So these days, but those numbers are gone up. They actually, like one more thing which you could actually notice is that when you misspell it, but still it actually understands it, right? And the reasoning is because of this tokenization part of it. So it is actually dividing it into the multiple words to it and things like that. And what they conveniently did is that when they started with these tokens, 50,000 tokens, they created one couple of tokens called as unknown tokens. If something unknown things comes in, you will just put that as an unknown. And you hope that, okay, it will be able to understand it using the context part of it, right? Attention mechanism. It will understand all the other things which is around that word, we can understand what is the context is all about and then predict the next word. So that is what has happened. When there are so many of such kind of data which is coming in, and you can't represent it, they can change it to the tokenization side of things. So these days, the tokenization is another area. Embedding is another area where it is actually a lot of research is happening. So how big the dictionary should be, how many vectors is required for it. So when you do this public information, which doesn't have it in over there, this information, whatever you are scraping from the web, can be represented in these matrices. So it is already there in that models. It has seen enough of those learnings. So this is one more challenge is because of this, right? Like when you have this information, it may not be encoded in the feed-forward network. It is a new information which is coming in. So hallucination can happen a lot. So you need to have that is another topic itself. But yeah, this is where you need to be very clear about, okay, where these facts are, from where you are getting the facts. Is it facts from you, what you provided, or it from your internal knowledge, what do you have it inside this? Yes.
This is about vocabulary. So the tokenizer has a vocabulary, right?
Correct. Yeah, that is the right word. Okay, 50,000 vocabulary size. Yeah.
So I wanted to ask how the size of the vocabulary impacts the model's capability.
Okay, so
this is coming from, so recently Opus 4.7 came.
Correct.
And it is using more tokens.
Correct.
Because the tokenizer and the embedding models are different for it.
Yes.
Obviously the capability is better, but does it have a correlation directly with the model capability?
Yeah, definitely it has. So there is a law called scaling law. So the more the parameters, when more the information, so you can actually embed more information into the systems. So that is how the LLMs have been actually, whenever a new model comes in, you feel that, okay, its power is really high because the number of parameters what they have is increasing and increasing and increasing. And how does that parameters increase? One say is this vocabulary size. The second is the vector representation, what is there. These two things defines the entire size of the models.
I think number of parameters also.
The parameters, that numbers is coming from this one. So for example, feed forward network is actually for the times of the vector representation of it, right? Say for example, in this case 12,000, it will be feed forward network dimension will be around 49,000. So when you see that in a matrix, you have a 2 by 2 matrix, you have 4 parameters to tune, right? So when you have a vocabulary size of 50,000, you have 10,000 of the vectors, suddenly you have a parameter of 50,000 into 10,000, 500k, right? That parameters which you can actually tune, right? So now if you increase the vocabulary size, there are more parameters to tune it. But the importance of that is that when you are tuning the informations, there is a concept called as overfitting. You need to have enough data to tune it. So you can't say that, okay, today I'm going to, even though I have an infrastructure, I can't say that I'm going to create a model which is the size is around 100 trillion tokens, because I wanted to encode every single informations out there into existence right now, because we don't have enough data to that. So if I do that, it will start overfitting these informations. So vocabulary size has a say in how many parameters at the end of the day it comes in. So it actually both this, right, vocabulary size as well as how many representation, how many words of, how many dimensions of each embedding has how many dimensions each embedding has a say in total number of parameters what is there. So yeah, so and tokens, the more you could actually if you think about tokens, the characters, like each word, each character, it becomes a token. Let's assume that each character is a token. Then you have a finite set of characters. If you are supporting only English and whatever it is, you always have a finite set of characters. So that is a minute level you can go. But then you will have more number of multiplications, more number of scale which is required to find out this. When you're doing the matrix multiplications, you need to do that many mathematical operations on it.
I think the meaning gets lost.
Correct. Even yes, exactly. So that is why I was saying that, okay, even that vector, how to tokenize it, how to embed it is itself is a lot of exploratory work, research work going on, and there are different types of algorithms to do that. So yes, 4.7 has 35% extra tokens. It regenerates more. So yeah.
One final question from me. So often these publicly available LLMs are doing the work. They are able to predict everything that we know. They have the entire internet database. They're being augmented also. So, but the daily practical use cases that we get, or we have to work with regulatory frameworks where there is limited data, fully closeted silos of information, which is where we should not let the data leak outside, and also we should enhance that. Like if I give a vague statement,
Yeah.
just AI it,
Yeah.
AI the hell out of it, right? So how do we make sure, like how do we select this maybe Opus 4.6 model where there is a lot of parameters, a lot of tokens, and a lot of vocab, which may not be relevant for our focus zone.
Correct.
So are there any ways where we can specifically use this set of facts only to determine the outputs? Don't get the entire universe in your knowledge base and try to predict an answer.
Yeah, that is an amazing one more expert talks, I would say. But in a very small, yes, you can actually do that. That is, some of the RAGs actually tries to do that. Okay. So RAG systems usually does like say that, okay, retrieve the documents and augment it in using the LLMs, but face that the grounded to the truth which you are actually retrieve from your informations. So what you are actually asking regulatory things like that, okay, you have a domain of like a very specific domain.
Yeah,
you need to
or fintech or whatever.
Yeah, fintech, let's say a lot of data are there and you want your answers to be grounded to it, you use those kind of mechanics to do that.
Right, okay.
RAG or even simple prompt engineering also do that. Like say for example, if you can actually put those, like say I have a PDF, right? And if you ask that today's world, if you go to Claude or any of those models, you upload that PDF and ask some questions about that PDF, right? Okay. It could be your portfolio performances. It can actually give those numbers because it can read it and then give that ground based on those information. Okay. So even prompt engineering, good prompt engineering can also do that trick to do that.
You were mentioning about a nano LLM in the beginning of this, right? So
correct.
When you have a specific knowledge database where you want to work with, maybe some you also want to integrate with external LLM models also. Does building a small sized models or nano LLMs, does that work?
No, don't try. To be honest, right? So that is very specialized thing. So to build an LLM or SLMs, the amount of data which is required is so high.
Okay.
So the best techniques what you can actually use is that, okay, maybe use a SLM and then fine tune to your domain.
Okay.
Right, there's very specific things, but again, those are the final optimization layer. You could actually get to 80% by using a general model and using a RAG or something, or prompt engineering itself. You can get to do 80% of what you really needed. So if you try to create a model by yourself, the infrastructure which is required for that, doing that, is so high. To give an example, I don't know whether you have heard about Sarvam AI, right? Like Sarvam LLMs, which has been created in India. They took 6 months of work which to create that models, and they had access to the government procured the GPUs.
Oh,
So the government provided them with GPUs to train on it, and then train on the informations which we have in this to create it, right? And that is only around 120 billion parameters, not even into these worlds of Claude and GPT. These days are in trillion parameters, right? So that is the scale of what we are talking about, and not everyone will have access to those kind of infrastructures. No, I would say 99% of people doesn't have access to those kind of infrastructures at this point in time.
yeah, understood. It looks very complex.
Yeah. So there's nano GPT or nano, that LLM which I was talking about, is a very vague to understand the concept of what is happening. So you will see about this vocabulary size and things like how it impacts it. Like we talk about this context size window. I didn't touch upon this talk about it. That also has a say in it, right? What does the context size window means and what happens when it is, right? Like what is happening and all those things. So yeah, so that talk is originated from learning about the concept. Similarly, this I would suggest this semantic word ladder, right? That actually helps you to learn about embeddings, right? And that will help you how the RAG system works, right? How the cosine similarities works. So these kind of small pet projects will help you to learn about the concepts of it.
Yeah, thank you.
Any other question? Cool, awesome. Thank you everyone. Thank you for coming over.